In today's video, we're going to learn about function operations, and we're going to focus on two main areas of function operations: composition of functions and inverse functions. So let's start with composition of functions. When we do a composition of function, we take f of g of x, or replace the entire g of x function into the f function, and then we simplify down. But before we actually work with composition of function, let's talk about the domain and the range of a compositional function. In this example, f of g of x, our g of x function is going to be substituted into the f of x function. So we're going to start with the domain of g of x. Those are the values that we can put into the function first. And then what comes out of g of x is called the range of our g function. Then we're going to put values into our f function, which is called the domain of our f function. And what values come out would be our range of our f function. What we're going to focus on, since we're putting g into f of x, we need to make sure that the range of g, the numbers that come out of the g function, will meet up with the domain of f. We have to check for any conflicts. If there's any numbers in the range of g that we cannot put into the domain of f, then we have to state that and limit our original domain. Let's try our first example. We're going to find g of f of x. So that means we're taking g of f of x, so all of f of x function is going to be placed in place of every x in our g function. So that means we will have the equation 2x minus 1 quantity squared. That's our f of g of x function. Now let's find the domain of our f function, our g function, and our g of f function. So f function is a linear equation, so our domain will be all real numbers. And because it's a linear equation, our range will also be all real numbers. And then we're going to take this f of x function and plug it into our g of x function. So let's look now at our domain and range of g of x. G of x is a quadratic equation, so our domain will be all real numbers because all x values work in that equation. But when it comes out, this is our parent quadratic equation, so that means our range will be all y values greater than or equal to 0. So let's write this down officially. So the domain of f is x such that x is all real numbers. The range of f is y such that y is all real numbers. Our domain of g is x such that x is the elements of the real numbers. And our range of g is y such that y is greater than or equal to 0. Now let's find our g of f of x. So we look at our range of f and our domain of g and see if there's any conflicts. Well, they're both all real numbers, so there's no conflicts. So that means our domain of g of f is our original domain. So that would be x such that x is the element of the real numbers. And our range will be our final output values with no conflicts. So that is y such that y is greater than or equal to 0. Let's try a little bit more complex equation. We're going to find the domain and range of f, g, and h. So f is a rational function. So our x value will be all real numbers except for 0, where our vertical asymptote's at. And our range will be all real numbers except for 0, because we have a horizontal asymptote at 0, since the degree on the top is less than the degree on bottom. G of x is a square root function. So only x values have to be greater than or equal to 0 to plug into this radical. Our range, well, it's a square root function graph, so our y values are always going to be positive, so greater than or equal to 0. F of x, h of x, is a quadratic, and so all x values go in there, so domain is all real numbers. Now notice this is a transformation down 1. So that means our y is greater than or equal to -1. Let's find the composite function f of g of h of x. So let's start in the most inside. We're going to take the h of x function and replace every x in g with h of x. So that just ends up being the square root of x squared minus 1. Then we're going to take that entire function and replace every x in the f function with that entire answer, which will therefore be 1 divided by the square root of x squared minus 1. Now we're asked to find the domain of our composite function, f of g of h of x. So we'll start with our most inside function, which is our h of x. Our domain of h of x is all real numbers. Our range is all numbers greater than or equal to -1. Then our g of x function, which domain is all x values greater than or equal to 0, and our range is all y values greater than or equal to 0. And then our third function is our f function. And recall that the domain of the f function is all numbers except 0. And our range is the same, all real numbers except 0. So let's first look for conflicts. Well, our range of h of x is from -1 to infinity, but we can only put numbers starting at 0 to infinity. So we have a conflict. We have some output values that cannot work. So I need to find all the x values in my original function, h of x function, that will give us an output value that is 0 or more. So we need to find the conflict. So we're going to look at our exceptions. If we look at the conflicts, when is our which values of x results with those conflict values, a y of -1 to 0, and then we're going to eliminate those from our domain. I'm going to do this graphically. So I'm using my transformations. I can quickly sketch the graph of x squared minus 1, which is a transformation down one. And I know the shaded region here is whenever my function is less than 0, between -1 and 0. So I want to set that equal to 0 to solve the equation. I know those key values there are that 1 and -1. So now I know that I need to limit my domain. Instead of using all real numbers, it's going to be all x values less than or equal to -1 or all x values greater than or equal to 1. So I've decreased my domain from all real numbers to this. Now I look at my g of x to f of x and see if there's any conflicts. And there is. Notice that I can't put 0 into this f function, but I'm getting an output of 0. So I need to figure out when would I get an output from that g of h of x function that is equal to 0. So let's figure out when our g of h of x equation equals 0. So I'm going to set the square root of x squared minus 1 equal to 0 and solve this equation. And I notice that this occurs whenever x equals plus or minus 1. So I can no longer have an x value of 1 or -1. So my new domain function is x such that x is less than -1 or x is greater than 1. The identity function is a function f that was composed with g, leaves g unchanged. So this means if I substitute a value into our function and our resulting equation is still the beginning function, I have what I substituted in was the identity function. So let's look at this example. Let's find f of g of x. So I'm going to replace g of x into place of every f function, and I get g of x. Now I'm going to do g of f of x. So x goes in place of every x in the 4x minus 5, which just gives me 4x minus 5, which is the original g of x function. Therefore, I know that f of x equals x is an identity function. A function f that was composed with g results in identity function f of x equals x is called the inverse function. So this is our test. if two functions are inverse functions of each other. Step 1, you would find f of h of x. And when we finish simplifying that down, if g of h of x is equal to x, then we move on to our step 2. And we find the opposite, h of g of x. And if that is also equal to x, then we can say that h and g are inverses of each other. The inverse notation that we use, so if we're given the function f of x, our inverse of f of x would be f to the negative 1 of x. We read that the inverse of f of x. The inverse of a function, a mapped onto b, is the relationship formed with the domain and range or interchange. So graphically, and we know that we can switch our domain and ranges when we have inverse functions. If the inverse relation is also a function, then the inverse function, f, and the inverse of f, we say are invertible. Key here is domain and range switches. Two functions are inverses of each other. Their graphs have reflection symmetry across the line y equals x. So look at this purple line. Let's look at some key values here. So this point is 2, negative 2, 4. So if it's an inverse function, our domain and range should change. So I should have the point 4, negative 2. We switch our x's and y's. Likewise, the point 2, 4 switches to become the point 4, 2 on an inverse function. So visually, this is a reflection across the y-axis. A reflection across the line y equals x. But notice in this case, our green function, our inverse graph, is not actually a function, because what was graphed here is y equals plus or minus the square root of x. So sometimes our inverses will not be functions, and sometimes they will be functions. So the only time they are a function is if the original equation was 1 to 1 and onto, then it has an inverse that is a function. One more definition, we say a function f is a self-inverse if the function and its inverse happens to be the same equation, or they're equal to each other. For this example, we're asked to find the inverse of f of x. So remember, step 1, replace the f of x notation with y. Since the definition of inverse functions that the domain and range switch places, we will then switch our x and y terms. Step 3, solve the equation for y. Step 4, check and see if the resulting equation is a function. If it is, replace the y with our inverse function notation. If not, then this equation does not have a function. So I'm going to do a quick sketch of this cube root function. It's a cube root function, move to the right 1, and I look at this, it does pass our vertical line test, so it is a function. So I'll replace the y with our function notation, and our answer is the inverse of f of x is the cube root of x minus 1. For our next example, we're going to find the inverse relation to the function y equals x squared plus 1, and then we're going to graph the function as inverse on the same set of axes. So we're going to switch our x's and y's, solve for y, and this is our inverse equation. So to check and see if these are functions or not, we're going to graph our original equation and our inverse equation. So y equals x squared plus 1 is a quadratic moved up 1. So our vertex will be at 1, and then we'll go over 1, up 1, then over 2, up 4, over 2, up 4 from that point. So these are my key values of the function x squared plus 1. Remember, inverse functions are reciprocals across the line y equals x. And remember that our domains and range switches. So I'm going to identify some 3 key points on this graph of f of x, or the graph of x squared plus 1. Now here's our line y equals x. And now I'm going to switch the x's and y's of these 3 key values and plot those points to help me sketch the graph of my inverse. Alright, so now we can see that that is a reciprocal over that, but one thing I notice is that my inverse is not a function because it does not pass the vertical line test. But what if I restrict the domain? I can make it a function by only graphing part of this equation. So we need to figure out how would I restrict the domain so that the inverse would be a function. Well, let's look at this one piece that's highlighted in the orange, highlighted in the purple. And when I reflect it, I get this highlightation in the purple, which does pass the function test, my vertical line test for function. So I'm going to redefine the domain of my original function as x such that x is less than or equal to 0. And that means our range will be y such that y is greater than or equal to 1. And so my inverse, remember we switch our domains and range. So my domain is my range of my function. So x is greater than or equal to 1. And my range is the domain of my function, original function. So y such that y is less than or equal to 0. The other way I could have restricted the domain is look at the other side of the parabola, which I'll highlight in green. And when I reflect that across the line y equals x, I get this other green section. So what would be our restriction of domain for this new function? Well, our domain is x such that x is greater than or equal to 0. Our range is still the same. Y has to be greater than or equal to 1. But now my inverse domain would be x such that x is greater than or equal to 1. Remember, I switched my domains and ranges. And my range is now the domain of my original function, y such that y is greater than or equal to 0. So how would I list this equation using these restrictions of my domain? So I'm going to state these equations. So I'm going to define y equals x squared plus 1 as my f of x function. And this first one, I restricted the domain so that x is less than or equal to 0. So I just place that on the f of x definition. And then when I do graph this, it does, that piece of the graph does pass the function test, vertical line test. So I would do it as the negative, the square root of x minus 1. Or I could have looked at this green part where my x is greater than or equal to 0, and it reflects up here above the x-axis. So that's not a reflection, it's just an x square root of x minus 1 graph. In our final example, we're asked to prove or justify algebraically that f of x and g of x are inverses of each other. So recall from earlier in the video that we talked about how to prove two functions are inverse of each other. The first thing you have to do is step 1. We're going to find f of g of x. And if that answer becomes x, I move on to step 2. So I'm going to quickly run through the algebra of finding f of g of x. If you need to, please pause the video so that you can follow all the procedures I'm doing as I'm simplifying this equation down. Alright, so f of g of x is equal to x, so this passed my first part of the test. So recall, if f of g of x equals x, we move on to the second test, which is now we need to figure out if g of f of x simplifies down to. If it simplifies down to x, we have inverses. If it doesn't, we don't. At any point, and when we're doing this test and we do not get x as our simplified answer, then the two functions are not inverses of each other. So again, step 2, we're going to find g of f of x. I'm going to algebraically do this really fast. So g of f of x means I take my f function and replace every x in my g function. So there's my x with my entire f of x function. And then we're going to simplify this down very quickly. And we find that g of f of x is also equal to x. So my conclusion, since f of g of x equals x and g of f of x also equals x, then we know that f of x and g of x are inverses of each other.